Welcome to Mrs. Merkel's physics class. Let's start with a prayer. In the name of the Father, and the Son, and the Holy Spirit. Amen. Ave Maria, gratia plena, Dominus tecum, benedicta tu in mulieribus, et benedictus fructus ventris tui, Iesus. Sancta Maria, Mater Dei, ora pro nobis peccatoribus, nunc et in hora mortis nostrae. Amen. In nomine Patri et Filii et Spiritus Sancti. Amen. Okay, let's get started. We're going to start a new unit, and it's electricity. So I have some notes written out here. I already sent out the crash course video, so hopefully you watch that so you have an idea, but she does go very fast. So I want to go over some electricity concepts with you today, and then we'll have a worksheet. So let's take a look here. We're talking about static electricity and basically electric forces in general. Electric forces between atoms. Electric forces between atoms and molecules hold them together to form liquids and solids. So obviously electric forces are very important because we need to have liquids and solids, okay? There's also electric forces in our bodies. Like think about in any like medical show and the person's heart stops and they come along with the paddles and zap them, okay? So there's electric forces in our bodies as well, which is really important. So it's important that scientists have studied electricity, and we're gonna just kind of do a little bit of an overview here to get started, okay? We experience static electricity when we comb our hair or when you touch the doorknob and it shocks you after walking across the carpet, okay? So we know what static electricity is and we've observed it, but let's keep talking about static electricity and how that happens, okay? So in each case, in the case of the combing of your hair or in the case of the doorknob, in each case, the object has become charged, whether it be the comb or whether it be yourself, okay? The object has become charged, and as a result of rubbing it, because the comb is rubbed against your hair, your socks are rubbed against the carpet, okay? So it's become charged. It has a net electric charge, okay? So that's what we're going to investigate, okay? And there's two types of electric charge. So we can tell this because the thing is that the scientists, they didn't know anything about this, okay? So they can tell because charged objects, when they're brought close to each other, either attract or repel each other. Okay, so we know that the charges are different. That's what they knew to start, that there was two charges and that they were different. Okay, so let's take a look, and depending upon the material, an object will either have a net positive charge or a net negative charge, okay? So let's take a look at the cases here. This case here, I have two charged plastic rulers, okay? So if your plastic rulers are charged, they're going to repel each other. You put them close to each other and they're going to try to push away from each other, okay? Two charged glass rods will also repel each other. If you put them close to each other, you're going to feel them pushing away from each other, okay? But if you take a charged ruler and a charged glass rod and you put them together, they're going to be attracted to each other. They're going to pull towards each other, okay? So let's keep going on with this. Okay, so the charge on the glass is different from the charge on the plastic. Turns out that scientists found experimentally that all charged objects fall into one of two categories. So there really is only two different charges, okay? The first type of charge, it's attracted to the plastic, but it's repelled by the glass. The second type of charge would be attracted to the glass and repelled by the plastic, okay? So now you're thinking to yourself, okay, wait a minute. How come I haven't been more specific? Well, I'm about to be, okay? There are only two types of electric charge, okay? And we know that unlike charges attract and like charges repel, okay? This is what scientists were experimenting with, and they didn't understand, and they were trying to understand. So let's see what they came up with. Okay, so it was actually Ben Franklin. You remember the guy with the kite? Ben Franklin named the charges. The charges are arbitrary, but what the names that he used are the names that we still use today. Okay, so he named, when you have a glass rod that's charged, he called that a positive charge. If you have something that's plastic, like a plastic ruler that's charged, and that has a negative charge. And those, so if something is positive, okay, then it has a positive charge. Like charges will repel, okay? Unlike charges will attract, okay? All right, so let's talk about the law of conservation. It says that the net amount of electrical charge in any process is 0. Wait a minute. What does that mean? Okay, the net amount of electric charge in any process is 0. Let me show you an example. So let's take a look. Let's say you've got a plastic ruler, okay, and you're taking it and you're rubbing the cloth on the plastic ruler, okay? The plastic ruler acquires electrons, so it requires a negative charge, okay? And the cloth acquires an equal amount of positive charge. So the net change, the net electric charge in any process is 0, okay? So whatever whatever electrons that the ruler got, the cloth lost them, okay? It's an equal amount. Does this law of conservation sound familiar? Yes, because we have a law of conservation of energy too, okay? So this is another way, if you look down here, another way to state the law of conservation. This one actually looks a little bit more like the energy one. It says, no net electric charge can be created or destroyed. Okay, same thing about energy. We cannot create or destroy energy. We can only move things around. Okay, so now let's talk an atom. Okay, so I've got a horribly drawn atom here. Okay, but for an atom, we have a positively charged nucleus. And then we have these electrons that are going around the atom. And the electrons are negatively charged. Okay, so it holds together in this unit. All right, so let's take a look. Let's talk about our atom now. Okay, so if you have a neutral atom, that means it's not charged at all, it's just neutral. A neutral atom has an equal number of protons and electrons. Okay, so let's say what we can do with a neutral atom is, if a neutral atom loses some of its electrons, okay, it has a net positive charge. So if some of those electrons are drawn off, the atom is now going to have a net positive charge because it has more positive than negative, okay? If it gains electrons, it has a net negative charge, okay? So when this happens to a neutral atom, whether it has a net positive charge or a net negative charge, it has a new name and it's called an ion, okay? So when an object is charged by rubbing, friction, that's the one that we talked about, it only holds a charge for a limited amount of time, okay? That's why, okay? Why when you charge an object, does it only hold a charge for a limited time? Even if you don't touch it, if you don't do anything with it, it's just sitting there, it's still only going to have a charge for a limited time. Well, I can tell you why, and it's kind of cool. The charge leaks off onto water molecules that are in the air, okay? Why does it do that? Well, I don't know. I had to Google it. Water molecules are polar. Well, what does that mean? Well, I had to Google that too. Good for you, because I can explain it to you. Water molecules have an uneven distribution of electron density. So I'll just give you a quick gist of what it means for the water molecule to be polar, okay? So what it means is, in a water molecule, there's a partial negative charge near the oxygen atom, and there's a partial positive charge near the hydrogen atom. So this uneven distribution is what causes a water molecule to be what we call polar, uneven distribution of electrons, okay? So let's now take a look at our plastic ruler again. So this is a charged plastic ruler. So remember, when you charge a plastic ruler, it has extra electrons, okay? So it has a net negative charge, Okay, so those extra electrons are attracted to the positive end of the water molecule. So they jump off the plastic ruler and they jump onto the water molecule, which has the positive side of the water molecule. Okay, so similarly, let's take a look at a glass rod. Okay, when the glass rod is positively charged, it's not going to hold its charge either, okay? Because the loosely held electrons from the water, okay, jump to the glass rod and neutralize it, okay? So let's take a look. Dry days, static electricity is more noticeable because the air contains fewer water molecules, okay? So there's less of that leakage, all right? But let's say it's a humid day and there's a lot of water molecules in the air. It's difficult to make an object hold charge because those electrons don't stay, or so that's how that works. That's kind of neat. Okay, let's take a look at the next one here. All right, we have two types of materials that I want to go over, okay? The first type of material is what we call a conductor, something like metal. In metal, the electrons are bound very loosely, and they're actually called free electrons, so they're free to move, okay? The other type of material is an insulator, like something like wood, and wood's electrons are bound very tightly, okay? So that's why things move in metal and they don't in wood. Most materials are either a conductor or an insulator. There's one special category, there's one exception, and for things like silicon and germanium, and those are what we call semiconductors. We're not going to get into those today, okay? So we talked about charging by friction, and now let's talk about other ways to charge objects, okay? So how about charging by contact? How does that work? Let's take a look, okay? So I have got a positively charged glass rod, and I'm going to take a neutral rod and I'm going to touch it to it. Okay, what happens? The electrons move over, okay, until from the neutral rod over here, the electrons move over until both have the same distribution of charge, leaving them both slightly positive. Okay, because when this loses some electrons, this neutral rod is going to become slightly positive. But this one's this one's still going to be slightly positive, not as positive, but it'll be positive. So we just charged by contact by doing that, okay? Because we took a positively charged rod, we bring the neutral rod close to it, and the electrons move over from here over to here till both of them are slightly positive. And then we just charged by contact, okay? How about charging by induction? She talked about this in the video too. Let's see how charging by induction works, okay? So we have a positively charged rod, okay? And we have a metal conductive rod, okay? So we don't even have to touch with this. All we have to do is we have to bring the positively charged rod close to this metal conductive rod. And what's going to happen is the electrons are going to move over. Okay, so what that means is when the electrons move over, this half of the rod that's over here, because remember, opposite charges attract, this half of the rod is going to have all the electrons, and then this half of the rod over here is going to be positively charged. Okay, and then, so listen to this, this is cool. We now have a polarized rod. What does it mean to have a polarized rod? It's exactly the same thing. It's an uneven distribution of electron density. It's exactly the same thing like with the water. They said the water had an uneven distribution of electron density. Well, now our rod, because these electrons moved over to this end, it's a polarized rod, okay? So what if we now, at this point, cut the rod in half, okay? So if we cut the rod in half, we have one positive side and one negative side. And by doing that, we just charge that rod by induction. And we never even had to touch it, okay? So we have charging by friction, charging by contact, and then charging by induction, which I don't even have to touch them, okay? All right, let's take a look. Earth is neutral, okay? So if you bring a charged rod into contact with the earth, the charge leaks into the earth, and that's called grounding, Okay, that's all. I just wanted to go over that definition on with you there. Okay, let's take a look at an electron. Electron has a charge of negative 1.6 times 10 to the negative 19 coulombs. And they say, as a scientist, you have really made it when your last name starts with a lowercase, because his last name was Coulomb. We'll talk about him in a minute, okay? So an electron has a charge of negative 1.6 times 10 to the negative 19. A proton has exactly the same charge, it's just that it's positive, 1.6 times 10 to the negative 19 coulombs, okay? So how many electrons are in 1 coulomb? Let's take a look. 1 coulomb is actually pretty darn huge. Let's take a look. So if I take 1 coulomb and I divide by the charge, 1.6 times 10 to the negative 19, there are 6.25 times 10 to the 18 electrons in 1 coulomb. So that's a pretty big unit, okay? Charles Coulomb, he was a French scientist, and he investigated electrical forces, and he found this equation. He found that the forces were related. And this actually looks like one of our other equations, too, for force, that we learned before. But let's go into this one. So the force between two charges is equal to K, which is what we call Coulomb's constant. We'll talk about that in a minute. Q1, the charge of the first one, times Q2, divided by R squared. K is what we call Coulomb's constant, and that varies depending on the material, okay? Depending on the material that your charges is in. Usually our charges are in air, and R is the distance between the centers of those charges, okay? So that is what we call Coulomb's law. This is here, Coulomb's law, okay? And K in air is 9 times 10 to the 9th Newton meter squared over Coulomb squared. The K that we use will always be in air. So this is K, 9 times 10 to the 9th Newton meter squared over Coulomb squared. All right, we're on the last page of notes. You're almost done. All right, if 1 coulomb were placed on, I'm not quite ready for an example. Okay, if there was a 1 coulomb charge that were placed on 2 objects that were 1 meters apart, it will result in 9 times 10 to the 19th 10 to the 9th newtons, okay? So that is absolutely huge, okay? If we put 1 coulomb on 2 objects, that force between them would equal the weight of almost 1 million tons. So basically what we're saying is 1 coulomb is huge, which is what I said before, okay? So a better unit is what they call the microcoulomb, and this is the unit there. So 1 microcoulomb is equal to 10 times 10 to the 6th new coulombs. So when we're talking about it, usually we're going to talk about microcoulombs, okay? Let's take a look at an example. Okay, so let's say I have 2 electrons that are 1 nanometer apart, okay? So this electron has a charge negative 1.6 times 10 to the negative 19, same here. A nanometer is just 1 times 10 to the 9th meters, all right? So we're going to take a look at Coulomb's law here. F is equal to K, Q1, Q2 over R squared. We know K is 9 times 10 to the 9th. We know the charges, and we divided by 1 times 10 to the negative 9th meters squared. Don't forget that. Make sure you put that in parentheses if you put it into your calculator. So the force between 2 electrons is 2.3 times 10 to the negative 10 newtons. Okay. The sign is positive, so the electrons repel each other. So if you're looking at an atom and you've got 2 electrons, the sign is positive, so that means that the electrons they match. So remember, when they match, the forces repel each other, okay? So when the sign is positive, the electrons will repel each other. If the sign is negative, that means that they're going to attract to each other. Okay, I hope you have a bit of a better understanding on electricity. Hopefully I didn't go quite as fast as the crash course, and maybe just seeing it again or presented in a different way will help a little bit more with understanding. I'm finishing up a worksheet right now. I just need to make an answer key, and I'll try to get that out as soon as possible. and we'll just have that. We are coming to the end here. My plan is I've got a really cool static electricity lab, which will really pull all of this together, help us to understand a little bit better, and that'll probably, we might have one more worksheet and then probably the static electricity lab, and that'll be basically in lieu of your final. So that'll help, but I really think it's going to help pull the concepts together for electricity. So, all right, that sounds good. Enjoy your weekend, and I will see you on Monday. Bye-bye.